Good afternoon, friends. Last few lectures you might have seen, I have kept on talking about static stability, control, CP, aerodynamic center, CG. I think too much I have talked. So before I start, what is the contribution of wing or tail or a fuselage towards making an aircraft statically stable, and also it can be trimmed at positive angle of attack. We'll just quickly glance through what we have learned, maybe in 5 minutes time, and then try to formulate the wing contribution, tail contribution and fuselage contribution in a manner so that it will help us in designing an aircraft. Okay? The basic question which comes to our mind, whatever I may be talking, stability, control, trim, etc., basic question is, can I fly this airplane, a particular airplane, at a particular CL? That means a particular alpha at a given velocity, at a given altitude. That is the question. And what we learned in a nutshell was, if I am talking about longitudinal part, longitudinal stability, that is angular motion in the vertical plane, and we have seen that Cm versus Cl or Cm versus alpha. By now we know Cl and alpha are related through some scalar term. So this variation should be like this, where the slope at the equilibrium here should be less than 0 or it should be negative. This is 1. And we know that for a statically stable airplane, that is, I need to see the slope at the equilibrium. Equilibrium, this point is because Cm is 0. At this point, I have to check that dCm by d alpha is less than 0, so it's statically stable. Also, I have to ensure that if I should trim at a positive alpha, then not only the slope, I should have a defined Cm naught, Cm at alpha equal to 0. Okay? If I could generate that, then I am happy that my airplane, the moment it goes to that alpha, the requisite velocity, and then it will automatically generate Cm naught, because the configurations are laid out like that. I need not put any elevator at that point, and that is a very efficient way of flying, because if you put elevator, it will have some drag. Okay, now the question comes, if I need Cm naught of the aircraft to be some value, then who will contribute towards this Cm naught? Naturally, I know Cm naught because of fuselage, Cm naught because of wing, and Cm naught because of tail. They are the three contributors. Of course, in a relative sense, we can say this is negligible compared to other two. That doesn't mean it is 0. So that is this Cm naught, Cm at alpha 0. Then similarly dCm by d alpha, the whole aircraft, which is about CG, we haven't forgotten that, about CG, the contributor will be Cm alpha fuselage, similarly Cm alpha wing plus Cm alpha tail. But you can very well appreciate that the Cm alpha, the static stability part, we are expecting it primarily from the tail, because this is also called, and that is why this is also called horizontal stabilizer. Okay? Wing, we are not expecting too much from stability point of view, because wing, we say, oh dear friend, your primary job is to produce lift. That's all. And fuselage, what is his primary job? His primary job to contain the passenger, cargo, it's a volume, right? So we are very clear that fuselage has a distinct role, wing has a distinct role, and tail has a distinct role. When it comes to stability, it is the tail, horizontal tail for longitudinal stability. Now our question is, can I formulate so that I know what are the parameters that control the contribution towards stability and contribution towards Cm naught? And that is the purpose of today's lecture. Let us draw a schematic of wing location, tail location, So let's say I have installed the wing like this. It's a little exaggerated, but we'll understand its purpose. And let us say this is a relative air coming like this, V. And let's say this is the aerodynamic center. And I call this angle as IW, that is wing setting angle. What is the center line? Well, actually, if I draw it like this is the fuselage going on like this. So I call this line as fuselage reference line. So in short, it is FRL. Okay. So what is wing setting angle? It is the chord line, how much angle it is making with the fuselage reference line. So I call this angle, velocity vector, and the fuselage reference line as alpha FRL, and this angle is already IW, wing setting angle. So total angle, velocity vector to the chord line, this will be alpha of the wing. Total angle, velocity vector to the chord line is the alpha of the wing. Then chord line making with fuselage reference line is IW, wing setting angle. This is called, let me write, wing setting angle. And this is, of course, is alpha FRL, alpha fuselage reference line. And we could see from geometry, alpha FRL is nothing but alpha W minus IW. This is clear? And let's say CG is somewhere here, because tail will be somewhere there, okay? And I say now this distance is jet CG, location of, vertical location of CG from the fuselage reference line. I'm putting symbol jet CG. Now along the x direction I am taking the leading edge of the wing, and from here, once I am measuring the CG location, I am calling it XCG. Similarly, from the leading edge, when I am locating the aerodynamic center of the wing, I am naming it as XAC wing. Is it clear? What is XAC wing? From the reference leading edge, what is the x distance of the aerodynamic center of the wing? What is XCG? It is the location of the center of gravity of the whole airplane. From which reference? From leading edge of the wing. What is jet CG? Jet CG is the vertical height of the CG. From which reference? From the fuselage reference line. This thing should be clear. If this is clear, now let me erase this part. You know this now. What is our aim? Our aim is to find out how much this wing will contribute towards pitching moment, to find out what is Cm alpha contribution because of wing, that is static stability part, and if at all it is contributing towards Cm naught or not. That is the question. What I was telling, we are trying to find out the contribution of wing towards Cm alpha, that is static stability, and Cm naught, which is essential for trimming at positive angle of attack. And we know that this contribution could come from wing, from tail, or from fuselage. So now we are trying to see what is the wing contribution and try to formulate. This diagram is now clear to you that this angle is wing setting angle, the chord line, how much angle it is making with fuselage reference line, the fuselage reference center line of the fuselage. So the wing is not set like this, please understand. Generally we have, this is the wing is set like this, right? So the wing setting angle is 0. Now wing is set like this with respect to the fuselage center line, okay? And this is alpha FRL, fuselage reference line, and this total angle from chord to the relative velocity direction is alpha of the wing. That is the angle of attack seen by the wing. Because of velocity, because of angle of attack, the wing is getting aerodynamic forces. Because cambered aerofoil wing, we are adding MAC of the wing also here. And this is a lift on the wing, and this is a drag on the wing. What is our aim? We want to find out what is the contribution of this force moment structure in terms of writing what is the moment about CG of the aircraft due to all these wing aerodynamic forces. Very simple. So now if you see here, I can easily write, let me write this equation so that I can explain it better. Do not worry about so many terms. You will find soon we'll neglect them and make our life simpler. Let us see one by one. This LW I can resolve in two components. One component here, that is LW cos of this angle. This angle you could see easily is nothing but alpha W minus IW. So this vertical component is LW cos of alpha W minus IW, and the moment term is what? Moment term is up to this point, from here to CG. But you know, from the wing leading edge, this total distance is xCG, and from wing leading edge, the AC distance is xAC. So this distance is nothing but xCG aircraft minus xAC of the wing. What type of moment this will give? This is acting vertically up. About CG it will give nose up moment, right? So this is positive. Second, you could see for drag. Drag also have two components. The vertical component, if you see here, this will be the 90 minus of alpha minus IW. So the cos will become sine. So we have dW sine alpha W minus IW into same xCG aircraft minus xAC wing. Similarly, you could see that LW has a horizontal component which is here, which is the sine component, which is here, LW sine alpha W minus IW. So this is acting here, the CG is over the fuselage reference line. So this also will give a nose up moment. So it is here positive. As far as drag is concerned, you could see the horizontal component is in this direction. Okay, that is dW cos of alpha W minus IW, but this component will give a moment about CG in the nose down direction. So this component has a negative sign here, and also of course you should not forget MAC of the wing because it's a cambered, or in general you have assumed a cambered wing. Okay, clear? All of you can write yourself this equation. But what is our aim? Please remember, let's not lose our insight. Our aim is CMCG versus alpha we want to plot, and we are checking the slope, whatever desired slope we want, how much out of that desired slope wing is contributing, and how much whatever CM naught we require, the whole aircraft, how much the wing is generating or contributing. So we'll be talking in terms of CMCG. So from MCG, how do I come to CMCG? You know, you are expert now. This is MCG divided by half rho V square S of wing into C bar. C bar is because CM is a moment, MCG is a moment. So this is dynamic pressure into area force into a length is moment, so that it becomes non-dimensional. Okay? So if I divide by half rho V square S C bar, what should I get? If you divide by half rho V square SW C bar, then MCG will become what? MCG will become CM CG. Of course, this is of aircraft. This will be equal to what? See, half rho V square S will come here, half rho V square S W. So this will become what? This will become CL wing by definition. Then this C bar, which is left, that will come under this. So I can write this is equal to CL wing into cos of alpha wing minus IW into X CG minus X AC wing. This is of aircraft, and bar, I am putting bar because now they are divided by C, or in fact divided by C bar. If I divide every term by this, similarly second term I will get plus CDW into sine of alpha W minus IW into X CG aircraft bar minus XAC wing bar. Bar means XAG distance divided by mean aerodynamic chord C bar That happens because I was dividing mcg by half rho v square sw c bar. That is, I'm taking that to the last expression. Similarly, the third one will be CLW into sine of alpha W minus IW into ZCG bar. Again, ZCG bar means ZCG divided by C bar. And the last term is CDW into cos of alpha W minus IW into ZCG bar plus CMAC wing. Do not forget this. It's a very important element. So let me start writing this expression only so that we can focus more on this. What do we say now? Let alpha W minus IW is very small. So cos of alpha W minus IW tends to 1. Also, see here, we also try to simplify it further. We are not happy just this term will become 1. We say CL by CD of the wing, okay, is such that CL of the wing is greater than CD of the wing. So we'll also plus alpha wing minus IW is small. Our aim is very simple. We want to make a cleaner term. We want to get rid of this. Okay? We want to make sure this becomes 1. Still life is complicated. We say let's assume that the CG is on the fuselage reference line. So this gentleman becomes 0. So this also goes. This also goes. Okay? ZCG 0 means the CG is on the fuselage reference line, which in any case the airplane will try to do that, right? Okay, so after cutting so many terms, what is left to us? We have CM, CG of the aircraft equal to CL wing, because this man is 1, into X CG bar minus X AC bar plus CM AC wing. That's all. Life is so simple. I told you we'll handle this, use term. Let us try to give an interpretation to this. What is this CMCG aircraft? That is the non-dimensional pitching coefficient about CG of the aircraft because of the wing. So I'll put a notation wing also so that you understand this is the contribution because of the wing. What is the XCG? XCG is of the whole aircraft. So I put aircraft. If this is clear, now let us do further simplification. I don't want to carry too many expressions. So what were the assumptions to get this neater expression? That alpha W minus IW is small, CL is much larger than CD, that is CL of the wing is much larger than CD of the wing, and ZCG is 0, that is CG is on the fuselage reference line, which are very realistic assumptions. Now, if this is the expression, we also know CL of the wing I can write as, because we have taken a cambered wing, CL naught plus CL alpha into alpha of the wing. Okay, so we substitute here. Instead of CL wing, we will be writing CL naught plus CL alpha of the wing into alpha wing. So this is CL alpha of the wing. This should be careful. So if I do that, then what I get? I get CM about CG because of wing is, of course, CMCG, when I say A dash C means of the aircraft, which is redundant, it will be equal to CL naught plus CL alpha of the wing to alpha of the wing, that becomes CL into XCG bar of the aircraft minus X AC of the wing. Correct? So this further I can write as CM CG of the wing, or I read differently, CM because of wing about CG of the aircraft, okay, is CL naught, and of course somewhere, and yes, CMAC of the wing is also here. Let's not forget about this. You will see this will play a magical role. We have a tendency to forget this friend, but he could be one of our worst friend. can create problems, so don't forget it. So if I do this, what I get? CL naught into XCG aircraft minus X AC of the wing plus CM AC of the wing, I put at one term, plus CL alpha of the wing into X CG of the aircraft minus X AC of the wing to alpha W. Right? Look at this expression clearly. I can now write this as CM about CG because of wing, CM about CG of the aircraft because of wing. I can write as CM naught wing plus CM alpha wing into alpha wing. Then what is CM naught wing? This is coming to be CL naught to XCG bar minus XAC wing plus CM AC wing, and CM alpha wing is coming out to be CL alpha wing into XCG of the aircraft minus XAC of the wing. Okay, now focus here. Immediately you think, what is our aim? You should not lose the insight. This is the CMCG, and here's the alpha. We wanted the slope to be a particular value. We want a CM not to be a particular value. We are trying to see how can I model how much wing will contribute towards CM naught, how much wing will contribute towards CM alpha. That is why slope, how much it will contribute, decided by this expression, how much CM naught, decided by this expression. Clear? What does it say? See the first expression. Let's see the CM naught expression. Let us be very clear that we want CM naught from the wing to be positive. Definitely not negative. Okay? At the most 0. But why should I have negative? Because if it is negative, I won't be able to trim at positive angle of attack. So overall CM naught I want positive. So I will always look for CM naught because of wing to be positive, whatever small amount it could be. That's all. I will never like it to be negative. Okay? Now see what is the meaning of this. Suppose this is the line, and let's say this is the wing, and this is the AC, and this is the CG. Let's say somewhere it is CG. I'm simplifying the diagram. What does it say? It says CM naught wing is CL naught, yes, at alpha equal to 0. There will be CL naught. And let's CG is here. So CL naught into this distance will give you a CM naught positive. So what is the meaning of that? Meaning of that is if you put the AC of the wing ahead of CG of the airplane, it will give a positive CM naught. In practice, what we'll find, AC of the wing and CG of the whole airplane will be somewhere very close. So this is the CG of the whole aircraft. This diagram is exaggerated to make you understand, but actually you'll find the AC of the wing and CG landing here, they will be almost very close, right? But what is important? If I want CM naught wing to be positive, then I must ensure that AC of the wing is ahead of CG of the aircraft. It is very clear from here. If AC is ahead of CG of the aircraft, then this distance XCG minus XAC will be positive. CL naught is positive. It will give positive CM naught. But what is the problem? See CM alpha of the wing. The moment I come to CM alpha of the wing, we know CL alpha of the wing is positive. No issue. What about this term? XCG minus XAC wing. This is also positive. So CM alpha is becoming positive. Okay? So actually the wing is contributing towards positive slope. So it is towards destability, or the wing is contributing towards unstable static stability. This is the correct statement. Okay? But we don't mind. Because we know, we have told you earlier also, wing primary role is to give lift. So whatever CM naught positive it has given, I am happy. Rest will take care from the tail. Okay. So now we come to the tail portion. So now we'll have tail contribution towards static stability. Before I go to any detailed expression, which I'll avoid, but let's understand one thing. If this is the wing, or in whatever way we have represented, the wing is having setting angle. We are also telling now the tail, which is symmetric tail, we are setting it at angle IT, which is called tail setting angle. But there is one point of difference that you must understand. That's very important. What we have seen, if there is a finite wing, because of pressure difference, there will be vortices that will give downwash, right? So if this is the velocity direction which wing is seeing, because of downwash being generated, the angle of attack at the tail will not be same as angle of attack at the wing. Actually, this velocity vector will not be parallel. It will be a little bit of tilted. Okay. If it was parallel to the wing velocity vector, whatever this direction is here, actually because of downward component, this vector will be tilted like this by how much? By epsilon, and which we call downwash angle. Okay. This is what should be understood. So if I try to write what is the angle of attack seen by tail, I will write whatever alpha w minus IW was there minus epsilon plus I of t. That's all. If there were no downwash, then angle of attack at tail would have been alpha FRL plus IT. But now alpha FRL is reduced because of epsilon here, because the velocity vector has tilted like this because of downwash. So this is the alpha tail. What is CL tail then? CL tail will be CL alpha tail into alpha of tail, that is CL alpha tail to alpha W minus IW minus epsilon plus IT. So this should be kept in mind. Rest things are similar. One thing you should understand, if this is the AC of the tail, then local lift here will be perpendicular to the local velocity vector, that is not with the free stream velocity vector, local velocity vector. So I draw a parallel to this, and there is a drag on tail, this is lift on tail, central line. However, when you are defining the CL for the whole airplane, then you will take the component of lift, drag, all in the free stream directions. Now, what is our aim? To find the moment. So this is jet CG. Since anyway we are doing all simplification, very common sense says, if these angles are small, what is the moment because of tail at the CG, about the CG? How much it will be? Simply because of a lift at the tail, lift because of tail into this distance from AC to of tail to CG. Let's say this is LT, so big LT into LT. What will be the moment? Moment will be primarily because of tail. I am assuming all angle to be small. Very common sense, you can understand that this lift force into this moment arm LT will give the moment. However, I put a minus sign because positive lift will give me nose down moment, and nose down moment is negative. As simple as that. So from moment, I can, from MT, let's say LT into capital LT. If I want to come to CMT, I am now an expert. I write LT into LT by half rho V square SW into C bar. So that will be my CMT. And what will be my LT? LT will be what? Lift at the tail will be what? That will be half rho V square. This is important. At tail, dynamic pressure at tail, which will not be same as dynamic pressure free stream. So I'm telling you, lift will depend upon the local condition. Into S tail, into CL alpha tail, into alpha tail, right? This is clear. Lift at the tail will depend upon the dynamic pressure at the tail, which is half rho V square tail, into S tail, into CL alpha tail, into alpha tail. And alpha tail, you know, is nothing but this expression. So if we use this CM tail is equal to minus LT, and for LT I write half rho V square at tail into S tail into CL tail instead of CL alpha tail into alpha tail. This divided by half rho V square free stream SW and C bar. You know CM tail now by substituting the value or expression of L tail into this expression. So I get CM tail as this. What is CM tail? It is the pitching moment coefficient because of tail about CG of the airplane, right? So this I can easily write as minus LT ST by SW C bar. This is 1 into neta into CL tail. But neta is the ratio of dynamic pressure at the tail and dynamic pressure at the wing. You can understand the dynamic pressure will be different. Suppose there is the engine exhaust falling on the tail surface, horizontal tail surface. So dynamic pressure ratio neta may become more than 1, but typically the value is around 1. And this is CM tail. The sign is negative for a positive CL tail, that is positive alpha. CM is negative, so it's a restoring tendency. And this is what the tail is supposed to do. It is contributing to our static stability. And the magnitude of static stability will depend upon this ratio LT ST by SW C bar, which is also called tail volume ratio or horizontal tail volume ratio. Tail volume ratio. This is for horizontal tail. You could very easily see that. What is LT? LT is the distance of AC of the tail from CG. So if I increase this LT, the restoring moment will increase, or for a given LT, I can increase the area of this tail, then also this LT into ST will increase, or increase both, right? So what we say as a designer, if we increase VH, this tail volume ratio, it will increase the static stability characteristics of the airplane. Okay. Now, if we do further some arrangement, we'll find out what we are actually trying to look for in terms of CM naught and CM alpha expression. So you have seen that. Let me write this step. CM tail equal to minus LT by C ST by SW neta into CL tail, and CL tail is equal to nothing but CL alpha tail into alpha tail is alpha W minus IW minus epsilon plus IT. I'll be quickly going with this derivation because this is not the main part of this part of the course. I will only touch upon few things so that I extract maximum thing in terms of design aspects. Okay? And here, what I can do for simplicity, I can model epsilon. What is epsilon? It's a downwash, right? Downwash is modeled to be function of angle of attack with the understanding as angle of attack increases, the lift increases. And lift means the pressure difference increases. So what is the strength increases? So they are linearly modeled as epsilon naught plus d epsilon by d alpha into alpha. What is epsilon naught? That even at alpha equal to 0, you can have a downwash, which is rightly so. If my wing is cambered, then at alpha equal to 0, there is a lift, there is a CL naught. So there is a pressure difference that will give also a downwash. That is epsilon naught. If the wing is symmetric, the epsilon naught value will be 0. So if I substitute here and then resubstitute the CLT here, I can get an expression which I will write directly here. What I will do now, CL alpha tail into this angle at the tail and expand epsilon equal to epsilon naught plus d epsilon by d alpha into alpha. Then I put this term here in this expression. Then I can show that CM naught of tail will be equal to neta VH CL alpha tail into epsilon naught plus IW minus IT, and Cm alpha tail as minus neta VH CL alpha tail into 1 minus d epsilon by d alpha. Okay? I again take you back. Please remember, we're trying to see how much tail will contribute towards adding Cm naught here and towards the slope. What is the first expression telling? You could see this is positive, this is positive, this is positive. Epsilon naught, suppose symmetric airplane, epsilon naught is 0. If I don't put any wing setting angle, this is 0. So how can I get positive Cm naught? If IT is negative, that means what? If IT is less than 0, and if IW is 0, if epsilon naught is 0, then if IT is less than 0, this implies Cm naught tail will be greater than 0. So I repeat, Cm naught tail expression we are seeing. This observation is very precise for a designer. I am looking for getting Cm naught contribution from tail. I know that even if the wing is symmetric, if I don't put a setting angle, I can get positive Cm naught by putting IT negative. IT negative means if this is the fuselage reference line, I will be setting the tail, horizontal tail like this. This is IT less than 0. Typically, this value will be around 2 to 5 degrees in aircraft. So one of the major contribution that comes from the tail is in terms of Cm naught. Here, tail also gives larger value here. About the slope, you see. About the slope, tail is very clear. Neta positive, VH positive, CL alpha tail positive, and there is a negative sign here. So as long as 1 minus d epsilon by d alpha is positive, it will always give Cm alpha tail negative, always stabilizing, and it is always positive. Typical value of d epsilon by d alpha maximum only 0.2. So we try to reduce this value by doing some configuration. So this is another interesting thing. I can go on changing the slope of this line by changing the value of VH. Suppose I wanted this slope, but actually the slope is something like this. Right? And to increase the slope, okay? Then I have to make it more stable, so I will increase the VH here. So I will increase the tail volume ratio. I will increase ST and into LT, ST separately or LT separately or both. So remember this typical value of VH. A good designer will take the value from 0.5 to 0.7 to start with. Just to complete this part, we have seen one thing. If it is Cm versus alpha, and this slope is for a particular CG, if I take CG aft, right? Okay, then I know this slope goes on changing, and there is a CG location at which the slope is 0, and we call it the aircraft at this CG location has become neutrally stable, and that CG location where the aircraft become neutrally stable we call neutral point. So we will try to formulate neutral point also. See, we know now Cm naught of the aircraft as Cm naught because of wing plus Cm naught of fuselage, which we have not derived any expression for that smaller value. Then neta VH CL alpha tail into epsilon naught plus IW minus IT. This is the Cm naught of the aircraft. Then Cm alpha of the aircraft. If I add up all, I get CL alpha wing into XCG bar minus XAC wing plus Cm alpha fuselage minus neta VH CL alpha tail into 1 minus d epsilon by d alpha. Typically Cm alpha fuselage will be positive, so destabilizing, but we have not estimated that, and they are very small values. What is our aim? We want to find what is that CG location of the aircraft where Cm alpha becomes 0. That is neutral point. Okay? So I can put Cm alpha equal to 0 and solve for xCg. So I'll get the expression of neutral point as xAc of the wing bar minus Cm alpha fuselage by Cl alpha wing plus neta Vh Cl alpha tail by Cl alpha wing to 1 minus d epsilon by d alpha. Okay? You could note very strongly here one point. There is general confusion. Neutral point has nothing to do with the CG location. So this neutral point will depend upon how the wing, tail, fuselage are laid out. It has nothing to do with CG. Okay? So for example, for a given layout, if this is the airplane, depending on what is the CL alpha of the wing, what is the CL alpha of the tail, where it is located, on this aerodynamic aspects related to the size, shape, etc., neutral point is decided. Neutral point, let's say, is coming somewhere here. Okay? What is the message to us? Message is, when you are doing a layout of your mass distribution, please ensure that first, that the CG of the whole airplane should not cross this. Because the CG comes here, the aircraft will become neutrally stable. Second question comes, you should know a priori how much should be this separation. How much ahead you should be for your stability and control purpose, because you know if this separation is too high, it will be very highly statically stable. So you need to have large control force to control it from one CL to another CL. You don't want that. So typically you will say, I want this separation to be 10 to 15% or maybe 5 to 15% of C bar. That this distance is typically 5 to 15% of the mean aerodynamic chord. And that is a quite good stability margin, and you can have your controls applied comfortably. So that is the concept of neutral point. Okay? And you can calculate neutral point if you know what is the AC of the wing, which you know it is at a quarter chord point. You know how to calculate CL alpha of the wing. You also know how to calculate CM alpha of the fuselage, although I have not covered. And these are numbers. So d epsilon by d alpha also you can calculate. So once I know those things, then I know what is the neutral point, and I will design my aircraft and lay out the component in such a way that CG is ahead of neutral point by 5 to 15% of mean aerodynamic chord. Okay? So this is the whole essence of stability and control. But next question what you are going to ask is how this neutral point and the control is linked. That is, I am telling again and again, if this is large, then control effort will be more. So that part also we will be talking in the next lecture. Then we will go for design. Okay, clear? Again, the preliminary part of design.